we have given a cylindrical magnet, and for this cylindrical magnet, its length is 4 centimeter, and diameter of this cylinder is 1 centimeter. And uniform magnetization Mz, and its value is given, which is 5000 ampere per meter. And again we have to find out the value of magnetic dipole moment, that means capital M, net magnetic dipole moment we have to calculate. In this numerical, Mz is provided. Again we know the formula. Formula for Mz is equal to M net divided by volume, and therefore we have to calculate net magnetic dipole moment, and this net magnetic dipole moment M net is equal to Mz multiplied by volume of the cylinder, because our magnet is in the form of a cylinder. So in this case we write M net, net magnetic dipole moment, is equal to Mz into volume of a cylinder, which is pi r square into L. So this is the volume of the cylinder, this is the magnetization of magnetic field. Again this formula can be written as Mz multiplied by pi. As we know that radius is the half of the diameter, then d by 2 and its square, that means here we write pi into d square divided by 4 and into length. So this is the formula for M net for a magnet which is in the cylindrical form, or which is in the form of a cylinder. And now if we substitute the values, then we get magnetic dipole moment is equal to Mz. The value of Mz is 5000 ampere per meter, and this 5000 ampere per meter means 5 into 10 to the power 3, multiplied by the value of pi, which is 3.14. Again the square of the diameter. Diameter is given 1 centimeter, and 1 centimeter is equal to 10 to the power minus 2 meter, and therefore we substitute this value 10 to the power minus 2 meter. And its square, d square divided by length. Length is given 4 centimeter, and 4 centimeter is equal to 4 into 10 to the power minus 2 meter, and total divided by 4. Now This 4 gets cancels with this 4. Then the remaining terms are 5 into 10, 3.14 and into 10 to the power, this is 3 minus 4 and minus 2, that is minus 6. And if we calculate this, the result comes out to be, if we multiply 5 into 3.14, we get 15.70 into 10 to the power minus 3, and its SI unit is ampere meter square. So in this numerical we have taken a magnet which is in the form of a cylinder having length, having diameter, and magnetization is given, and from this we have calculated the net magnetic dipole moment, which comes out to be 15.70 into 10 to the power minus 3 ampere meter square. Again, we take one example regarding the magnetization of material, and after that the second property, magnetic property of matter, we will discuss. So next numerical on this magnetization is, if a bar magnet made from steel having magnetic moment which is equal to 2.4 ampere meter square, and the mass of the magnet is given, and the mass of the magnet is 6 into 10 to the power minus 3 kilogram, and third data provided, which is the density of the steel, and the value of density of the steel is given, which is 8 into 10 to the power 3 kilogram per meter cube. And again, we have to find out our first magnetic property of matter, which is magnetization of material or intensity of magnetization, that is mz. As usual, the formula for mz is m net divided by volume, which is equal to m net divided by, as we know that density is equal to mass upon volume, and therefore volume is equal to mass upon density. So the value of volume is mass upon density, and therefore our formula becomes m net magnetic dipole moment multiplied by the density of the steel divided by mass of a magnet made from steel. And finally, if we substitute the values in this formula, mz is equal to m net, the net magnetic moment is 2.4 ampere meter square multiplied by density of the steel, which is given 8 into 10 to the power 3 and divided by mass, and mass is given 6 into 10 to the power minus 3. And after calculating this value, we get 0.4 multiplied by 8 into 10 to the power 3, and this 10 to the power minus 3, total power is 10 to the power 6, and which is equal to 3.2 into 10 to the power 6, and the SI unit for mz, which is ampere per meter. So today we learn about magnetization or intensity of magnetization, and with respect to this article we have solved 4 different types of numericals. Now, in the magnetic properties of matter, the second magnetic property we have to discuss is known as magnetic intensity. It is also a vector quantity and denoted by letter H. So magnetic intensity. So magnetic intensity is nothing but the strength of the magnetic field, which is a vector quantity, and this magnetic intensity H is given by the formula H is equal to mu by B, or this is equal to mu 0 upon B0. That means we define magnetic intensity H, which is the ratio of magnetic intensity H is equal to B by mu, or which is equal to B0 upon mu 0. So H is equal to B by mu, which is equal to B0 upon mu 0, and from this we define H is the ratio of magnetizing field B0 to the permeability of free space or vacuum. Again, this magnetic intensity H is nothing but which is equal to N into I. Now, the SI unit of this magnetic intensity is come out to be, we know the SI unit of magnetic induction or magnetic field is Weber per meter square, and the SI unit of mu 0 is Weber per ampere into meter, and therefore we write Weber per meter square multiplied by ampere into meter divided by Weber, and therefore this Weber gets cancelled. 1 meter is cancelled with 1 meter, and therefore the SI unit of H, that means magnetic intensity, is again come out to be ampere per meter, which is same as that of magnetization. or which is same as that of intensity of magnetization. Again here we have write the formula, which is H is equal to Ni, where N, this N means in case of a solenoid, as we have already studied in magnetic effect of electric current, solenoid, the value of this N is capital N divided by N. That means number of turns per unit length. That is N by N. Again, in case of a toroid, this N is equal to again N by N, but N divided by 2 pi r. That means the value of this N regarding the solenoid and regarding the toroid is number of turns per unit length. And from this formula, H is equal to Ni. Again we find the SI unit of this H, or H is equal to Ni, and the formula for Ni is again same, which is come out to be ampere per meter. So second property of matter is magnetic intensity, and this magnetic intensity is the ratio of magnetizing field and the permeability of free space or vacuum, or it is nothing but N into R, and having same SI unit as that of magnetization or intensity of magnetization. Now today, the third property of matter, magnetic property of matter, we are going to study. It is called as magnetic susceptibility. Magnetic susceptibility, and this magnetic susceptibility is denoted by the symbol like this, suffix M, and read as Km. So magnetic susceptibility denoted by the symbol which is Km, and this magnetic susceptibility is given by formula Km is equal to mz divided by h, or I divided by h. That means magnetic susceptibility is the ratio of magnetization of material to the magnetic intensity, or magnetic susceptibility is the ratio of intensity of magnetization divided by magnetic intensity. As this magnetic susceptibility is the ratio of two quantities, it has no unit and no dimensions. And again, this magnetic susceptibility is a scalar quantity. So the magnetic susceptibility is equal to mz by h, or I by h. Again, this magnetic susceptibility can be written in another form, and this another form is called Km is equal to mu r minus 1. So magnetic susceptibility is equal to mu r minus 1, where mu r is the relative permeability of the material. And our next article is to discuss about this relative permeability of the material known as mu r.